Olá, boa tarde a todo mundo. Sejam bem-vindos a mais um seminário do nosso ciclo dos seminários de departamento do IAG. Agradecemos a presença de vocês, acompanhando tanto pelo Google Meet quanto pelo nosso canal de YouTube. Hoje temos o prazer de ter a Anabella Araudo como palestrante. Agradecemos ela ter aceito o convite e ela vai falar sobre aceleração de partículas, amplificação de campo magnético e emissão de raios gama em jatos protostelares. Eu vou pedir a todos vocês, por favor, para desligarem seus microfones, sua câmera durante a apresentação. E se tiverem alguma pergunta, podem indicar isto no chat do Google Meet. Então, good afternoon, everyone. Thank you so much for joining us during this seminar, another seminar of the astronomy department. Today we have Anabella Araudo as a speaker, and we thanks her for accepting the invitation. Anabella got her PhD degree in astronomy in La Plata University, and since then she is working in institutions all around the world, such as the UNAM in Mexico and the University of Oxford in the UK. Then she went to Montpellier's Universe and Particles Laboratory in France. And 4 years ago, she's in the Czech Republic. First, she worked in the Astronomical Institute of Czech Academy of Science. And currently, she's in Eli Beamlines laboratory. She's also an active member of the CTA collaboration. She's interested in particle acceleration and non-thermal emission in the whole electromagnetic spectrum, shock particle acceleration, and magnetic field amplification in relativistic and non-relativistic jets. And today, she will talk about particle acceleration, magnetic field amplification, and gamma ray emission in protostellar jets. And before we start, I would like to ask everyone to please turn off your cameras and your microphones during the presentations. And the question will be answered after the talk. And if you have a question, you can indicate this in the chat. Well, Anabella, whenever you want, you can start sharing your screen.
Okay, thank you very much. Thank you for the invitation. It's a pleasure for me to give this seminar today with you. So I will share my screen. So is it okay?
Yes.
Okay. So as Maria mentioned, I will talk about non-thermal processes in protostellar jets, and this is a work in collaboration with Marco Padovani, Alexander Markowitz, Carlos Carrasco González, Ariana Rodríguez-Kamenetsky, and Luis Felipe Rodríguez. So the talk is organized as follows. First, I will give a short introduction about stellar jets, and then I will describe the non-thermal emission that we detect from these sources, in particular in radio. And then I will show you that in order to have the magnetic field that we need to explain this large flux in radio, we need some kind of amplification of the magnetic field. And in this work, we focus on magnetic field amplification by Bell instabilities. That is the same mechanism that is working in supernova remnants. So what we have done is to apply the same mechanism that it has been developed for supernova remnants, but in the context of protostellar jets. And then I will show you some prediction for the gamma ray emission of these sources, and finally some conclusions. So as you know, these massive stars are formed in these dense molecular clouds where you can see these pillars. These pillars usually are called pillars of stellar formation, are very beautiful structure that we can see with the Hubble Space Telescope at here. So this image is from Orion region. And you can see that here at the top of these pillars, we have these beautiful structures that we call it jets. If we make a zoom of this source, we can see here the central protostar that it is in the process of formation. And we have these beautiful and very collimated jets. And here at the termination, in the termination region, we have these bow shocks in both sides. So in this talk, I will focus in this kind of jets. I mean, jets from high mass protostars. I will not talk about jets from low mass protostars. So this is on a sketch of these sources. So we have the central protostar here that is surrounded by an accretion disk, and then we have this very collimated jet, and the jet there is an envelope that we call it outflow, and the outflow it is not very collimated, and also it is very slow. However, the jet it is well collimated and very fast. The formation mechanism of this protostellar jet it is quite similar than the formation mechanism that works in relativistic jets, like for instance in AGNs or microquasars. Let's say this Blanford-Payne mechanism. We have magnetic field in this accretion disk where particles can escape from the accretion disk like by moving in these open magnetic field lines. Concerning the propagation of these jets in the environment, has been a lot of work has been done, in particular by people by the group of Bete de Gouveia del Pino in Brazil, concerning the propagation of this, the formation, propagation, and also the importance of the magnetic field in the propagation of these stellar jets. Concerning the velocity of these jets, usually the way to know how fast are these sources, what people are doing is just measuring the proper motions. I mean, if the source it is quite it is on the plane of the sky, we can measure how these structures are moving on time, and then we can estimate the velocity of these jets. Typically, for low mass protostars, the typical velocities are between 50 and 200 kilometers per second. However, for the case of high mass protostars, the velocities are larger, like between 200 and larger than 1,000 kilometers per second. This is why we're interested in this high mass protostar, because as I will tell you later, we want to study non-thermal processes. This means like a particle acceleration in shocks, and because we're interested on particle acceleration by shocks, if these shocks are not very powerful, I mean the Mach number is not big enough, these shocks are not efficient enough for particle acceleration. And this is why we are focused in this high mass protostar. Also because the non-thermal emission has been detected in jets from high mass protostar in general. And this is why it is we believe that this non-thermal emission is due to particles accelerated in shocks. But I will go back to this later. So just remember that these high mass protostars, they have a more powerful jets. I mean, the shocks, the termination shocks are faster. And these sources, these jets from young stellar objects, usually sometimes we call it also Harvey-Harrow jets, are very well-known thermal emitters. And then this is why we can see in optical and infrared these beautiful images with the HST, with the Hubble Space Telescope. However, since the last 10 or 15 years, there are some observations in radio of non-thermal emission. I mean, it has been detected like in 20 sources, non-thermal radio emission, let's say synchrotron emission. And in my research, I am interested in this kind of sources, in sources that are non-thermal emitters in radio. So I will describe you. I will show you now some of the most famous, let's say, non-thermal protostellar jets. This source is Serpens, and you can see here. So this is the central protostar, and so this color map is a spectral index in radio, and you can see the central protostar. It is a thermal emitter. However, these nodes and the termination shocks here and here are non-thermal emitters. Let's say that the spectral index is between -0.2 and even smaller. Then we have this other source, this IRAS 16547. This source is this. It is very well known because it has a very well collimated jet and very elongated jet also. This is data taken by Luis Felipe Rodriguez and also by Guido Garay, where they detect non-thermal emission. And the way that we know that the emission is non-thermal is because, as in the previous case, the spectral index is negative. So here you can see that the central source is typically thermal source with a positive spectral index. However, the termination shocks in the north and in the south are non-thermal. The spectral index is negative in both cases. And this is the most, let's say, the most famous one, this HH8081, or let's say the source, it is IRAS 18162. However, this source is very well known because this Herbig-Haro object HH80 and HH81 has been detected since a long time ago, also with non-thermal emission in radio. But why this source it is so important now? It is because it is the first source where we have detected polarization in radio. So in all the other sources that I showed you before, and also in other sources, the way to know that the emission is non-thermal is because we measure the spectral index, and the spectral index is negative, and therefore we conclude that the emission is synchrotron. However, to be really sure that the emission is synchrotron, we need this polarization measurement because synchrotron emission is polarized, and this is the only source from where we have this polarized emission. You can see here this vector that shows that magnetic field is parallel to the jet, and so this is the sum of this region, this inner jet. And the equipartition magnetic field estimated by Carlos Carrasco Gonzalez, it is about 0.2 milligauss here. So in our for our study, we select non-thermal sources that has been detected by this that are available in the literature in these papers by Purser and Obonium. And we select in particular these sources from where we know the mass loss rate of the jet, that you can see that it is between 10 to minus 6 till 10 to minus 8 solar masses per year. I mean, this mass loss rate, it is quite large. And also with these sources, like the central sources, they have in some cases just one non-thermal lobe or two non-thermal lobes. And we select the sources with spectral indexes between, or let's say, this alpha between 0.3 and 0.7 or 0.772. I think it's the large, 78. Yeah, it's the largest. And from we know the flux in radio, the spectral index, the frequency that correspond to this flux, and also the size of the source. So typical sizes of these non-thermal lobes are, let's say, between 10 to 15 and 10 to 16 centimeters. One important parameter to study non-thermal processes, it is of course, the magnetic field. We will discuss later about the magnetic field, but also the density of the shed. So the most common way to estimate the density of the shed is just by considering mass conservation across the shed. And if we know the mass loss rate, that we know in our cases because we select sources where we know this mass loss rate. So if we know the mass loss rate, we fix the velocity in 1,000 kilometers per second. And also we can estimate the width of the shed because we know more or less the size of the synchrotron emitter. So we can, in that case, we can estimate the density of the shed in the termination region here. And it is like in most of the cases, we find velocity between 100 and 10 to 4 particles per cubic centimeter using this approach. However, there is an issue here that is the size of the non-thermal law, because here this is our synchrotron emitter. However, you can see that if this synchrotron emission it is not very well resolved, we can see that the emission it is much larger than the width of the shed, and therefore we can overestimate the width of the shed if we just assume that the width of the shed is equal to the size of the non-thermal law. And this is why here in this plot we consider we estimate this mass loss rate by using this equation here, but with two different sizes of the two different widths of the shed, and add these values here. And an upper limit of the shed density it is due to the free emission. I mean, let's say if these sources are non-thermal at a particular frequency, nu that it is this frequency here, here. At these frequencies, these sources are non-thermal. It means that the free emission has to be lower than the synchrotron emission at this particular frequency. So by imposing that the free emissivity is smaller than the synchrotron emissivity at a particular frequency, we can have an upper limit of the density in the shed, and add these values. And again, we estimate this upper limit by using two different sizes of the shed, like the width of the shed. And so what we can conclude from this plot is that these sheds are quite dense. Let's say the densities so this case, it is like the more extreme, the most lighter, I will say, like with densities between 50 particles per cubic centimeter till, let's say, 10 to 5. But other sources, they have much larger densities. I mean, the density range it is really large. Even with these upper limits are really upper limits, these values are quite large in all our cases. So let's say we will consider like a 10 to 3 as a canonical value for the density of these sheds from high mass protostars. And why this density is important? Because if we know the density of the shed, we know what is the energy budget. Like let's say we know what is the kinetic energy density in this flow that we can use for particle acceleration. We will use a fraction of this shed kinetic energy density to accelerate particles. And this is why we need to estimate, or we need some estimation of the shed density, because we need some estimation of the energy budget. And finally, this, as I mentioned before, all the sources in our sample are non-thermal sources. Therefore, the emission in radio is synchrotron. If we consider the synchrotron flux that we measure from these sources at this particular frequency, and this is the distance from Earth to the source, we can plot here what is the energy density in non-thermal electrons that we need to explain this synchrotron flux. As you know, the synchrotron emission is due to relativistic electrons interacting with the magnetic field. So here's the magnetic field. This is the magnetic field in the hotspots, let's say. And what we plot here, it is the energy density in non-thermal electrons, this parameter here, as a function of the magnetic field. And S is the spectral index. I mean, from that we can estimate this S from alpha, from the spectral index in photons. We can estimate the spectral index in the distribution of non-thermal electrons. And here, again, we plot this energy density in non-thermal electrons as a function of the magnetic field in the hotspot. And we can see that in most of the cases, we have magnetic field between, like, let's say, 0.05 till 10 microgauss. I mean, very large values of the magnetic field. These dots here, these orange and blue dots here, indicates where the energy density in non-thermal particles, I mean not only electrons, but electrons plus protons, is equal to the kinetic energy density. It means that, for instance, if the density of the shed is this, it is like, so here, I forgot to explain, this density here, that we call it this average density, it is the average density between the lower and the between the lower value here in this plot and the maximum value. So it is somehow the average value nearby here. So if this density is this average value between the lower limit and the upper limit in our estimation, we have that the magnetic field cannot be lower than these values here. Yeah? And if the density, it is the density estimated with the mass loss rate, then the magnetic field cannot be lower than these values indicated by these blue dots in this plot. So this is just to have an estimation of what are the values of the magnetic field in the hotspots. And again, you can see that these values are quite large. This is why what we conclude is that it should be some kind of magnetic field amplification in these sources. Now let's discuss what is the nature of this shock. So I mentioned before that in order to produce synchrotron emission, we need relativistic electrons. And one way, for instance, to have these non-thermal electrons in the source is because if there are some kind of non-thermal electrons accelerated by other sources in the molecular cloud, let's say if there is in this region some supernova remnants nearby where electrons can be accelerated and then escape and diffuse in the molecular cloud, then with this background, let's say non-thermal electrons can interact with the magnetic field in the Czech termination region and produce the synchrotron emission. However, this energy density in non-thermal electrons are much larger than the energy density in non-thermal particles in this molecular cloud. And this is why we need some kind of local acceleration of particles in the termination shocks, like let's say here. It cannot be just the compression of the plasma in the molecular cloud where these shocks are moving and compress the plasma there and therefore compress these cosmic rays there and increase the density of cosmic rays in this plasma. Because it is the energy density of cosmic rays in molecular cloud, it is much lower than these values here that we need to explain the synchrotron flux. So the conclusion is that we need some local acceleration and therefore the shocks cannot be radiative, because if the shocks are radiative, then the acceleration of particles, it is not very efficient. This is why we are interested in these adiabatic shocks. So the way that how we define adiabatic shocks in our model is by following the approach in this Blondin paper, where basically they consider the thermal cooling length, that it depends on the density of the shed and the shock velocity, and then they compare the thermal cooling length with the width of the shed. If the thermal cooling length it is larger than the width of the shed, the shock is adiabatic. In the opposite case, let's say here, when the thermal cooling length is smaller than the width of the shed, the shock is radiative. But we're interested in adiabatic shocks. Let's say if we set this condition, then what what we find is that the shock velocity has to be larger than these values. And this is why in our cases, because we don't know the jet velocities for our sources, because we don't have this kind of proper motion measurements. So we fix in all of our in our study this velocity in 1,000 kilometers per second, in order to satisfy this condition, and to be sure that that these shocks are adiabatic and not radiative. And why we want adiabatic shocks? Because we want to accelerate particles there. We want to explain this large energy density in non-thermal electrons that we need to produce these synchrotron fluxes in radio with local acceleration in this shock by the diffusive shock acceleration mechanism. And here this is just an example, or to see, I mean, the difference between the adiabatic and radiative shocks. You can see it in the case of adiabatic. In the case of radiative shocks, here, this case, we have this very dense layer here that is due to this compression of the plasma by a radiative shock. And then we will see at the end of my presentation that this layer, it is, even in the case we're interested in adiabatic shocks, we want to have adiabatic reverse shock. I mean, we want to have adiabatic reverse shock, or let's say a Mach disk. But then, in order to have a large, or in order to increase our emission in gamma rays, we will need a dense target here in order to increase our flux in gamma rays due to proton-proton interaction, for instance. And this is why our best configuration will be a combination of adiabatic reverse shock and a radiative bow shock, because we want to have this very thin, very dense layer here that it will help us for the gamma ray emission by proton-proton interactions. But here I just wanted to show you what is the difference from these numerical simulations presented in this paper, where they study both. They are more focused on radiative shock, but also they show this comparison with adiabatic shocks. And we can see that here, in the case of adiabatic shock, we have this very large cocoon, but we don't have it here in the case of radiative shocks. So this is our model. So this is the termination region of stellar jets. We have, well, I mean, this sketch also works in other jets, also in relativistic jets. We have a reverse shock in the jet, or Mach disk, and a bow shock in the ambient medium. But in our case, the ambient medium is the molecular cloud where these stars are being formed. And then, as always, the bow shock shocked material, it is separated from the reverse shock shocked material, or the jet shocked material, by this contact discontinuity. However, we will see that this contact discontinuity, in reality, it is not as here, but it is very unstable, and it is usually destroyed by instabilities. So this is our model, and here in this reverse shock, we accelerate the particles, and then these particles will produce the synchrotron emission in the reverse shock downstream region. And here, in this reverse shock downstream region, is where we have these large values of magnetic field that we have been estimated before, let's say about 1 milligauss. And what we're interested in, it is in magnetic field amplification of the magnetic field by Bell instabilities. So what are these Bell instabilities? The official name, let's say, it is non-resonant hybrid instabilities. However, everyone knows it as Bell instability because it was developed by Tony Bell in this paper, even when there is like some hints of this instability were published before in this paper by Bell and Czech 2001, but let's say the canonical paper is this Bell 2004. And what what they have done is basically they said if the acceleration of particles is efficient, let's say here we have this shock, and we have efficient acceleration of particles, we need to include this current of cosmic rays in the dispersion relationship. Or let's say we have to include this current in the MHD equation. And then when we solve this set of MHD equation, then we find this dispersion relationship, where we have this extra term here. Like let's say in the standard case, like let's say these alpha instabilities, we don't have this term. But when if this current due to cosmic rays is important, that somehow it is included in this eta parameter here, then we need to include this term. And what has been shown in this plot in this paper, it is that if we include this current, this force that is J cross B in the MHD equation, then after a while the magnetic field is significantly amplified, as you can see here. This is the magnetic field at T equals 0, and this is at T equals 20. You can see that there are very dense regions of magnetic field in the plasma. And somehow this theoretical idea of magnetic field amplification by cosmic rays came out at the same time where this data of X-ray emission from supernova remnants were also published. And the issue here is that these very thin filaments, X-ray filaments here, are very hard to explain by fast synchrotron cooling in the ambient magnetic field. Let's say the synchrotron, if we equate this, the width of these X-ray filaments with the synchrotron cooling length, that it is somehow proportional to 1/b squared, we need a very large value of the magnetic field in order to match the width of this X-ray filament with the synchrotron cooling length. And if we use the value of the interstellar magnetic field, where these supernova remnants are, let's say the typical value of the magnetic field in this ambient medium where the supernova remnants are propagating, let's say, we cannot match the width of the X-ray filament of these X-ray filaments with the synchrotron cooling length, and this is why we need this we need like a magnetic field, let's say, of about 100 microgauss to have this match. And this 100 microgauss is what you can have with this magnetic field amplification by cosmic rays, let's say by this Bell instability. So these Bell instabilities and this amplification mechanism for the magnetic field, it was the way to explain this very thin filament in the X-ray emission in supernova remnants. And also, because in order to, so we have this supernova remnant shock where particles are, you know that these supernova remnants are very efficient accelerators in our galaxy. And for a long time, people were discussing about what is the origin of these galactic cosmic rays, and supernova remnants were one of the best candidates to accelerate particles, let's say protons, up to the knee of the cosmic ray spectrum, let's say 3 times 10 to 15 electron volts. However, it was very difficult to explain with supernova remnants this acceleration till 3 times 10 to 15 electron volts. If we have this, efficient acceleration of cosmic rays, and we have this magnetic field amplification, we can see that only very young supernova remnants, let's say this supernova remnant with large shock velocities, can accelerate particles up to 3 times 10 to 15 electron volts. Other supernova remnants, let's say, these cases are for, like, let's say, not very large values of the shock velocity. And you can see that the maximum value that they get in this paper, it is lower than the value of the knee of the cosmic ray spectrum. We need shock velocities like, let's say, 10,000, 20,000, or even 30,000 kilometers per second in order to accelerate particles till 3 times 10 to 15 electron volts. And this is why the conclusion it is that only very young supernova remnants, where the magnetic field is amplified by this Bell amplification mechanism, are able to accelerate particles up to the knee of the cosmic ray spectrum. So this is a very, I wanted to show this example of supernova remnant because it shows very nicely how theoretical development match very well with observational achievements. So now we, in our work, we wanted to apply also this theory of magnetic field amplification by this Bell instability in the context of protostellar jets. The condition to have this non-thermal mode in the plasma is to have this parameter, let's say this eta, that we call it the efficiency parameter, multiplied by the Mach number square larger than 1. And then this parameter, it is this, and you can see that for typical values of protostellar jets, we have that this parameter, it is larger than 1 as required. So in principle, we can have these non-thermal modes in protostellar jets. And here what we plot is when we solve this dispersion relationship for typical values in protostellar jets. And here we plot the imaginary part of omega that gives us the growth rate. And we did it for 300, 500, and 1,000 kilometers per second for the shock velocity here. And we can see that in all these cases, and the density here is 10 to 3. It is not this value, but it is 10 to 3 particles per cubic centimeter in this plot. We can see that with all these velocities and 10 to 3 particles per cubic centimeter, we have this non-thermal regime in all the cases. Of course, this non-thermal, let's say, regime, non-resonant regime here, non-resonant regime, it is more important for the case of faster shocks. And here, this is the maximum growth rate, that it is this value here. And this maximum growth rate, it is important because it will we will need it to estimate the maximum energy of protons. And also we will see that in the case of protostellar jets, in some cases these jets are not completely ionized. And if these jets are not completely ionized, then this maximum growth rate decreases a bit, as you can see here. Like for instance, this line here is the maximum growth rate for the case of completely ionized plasma. Let's say ionization parameter equal to 1. But if we decrease the ionization degree in the jet, we decrease the maximum growth rate. And this is what we have plotted here. I mean, we solve the dispersion relationship by including this ion neutral collision frequency, and this is what we get. That if the plasma it is not completely ionized, the maximum growth rate is decreased, but the instability is still there. It is not damped. And so these calculations show that this magnetic field, that is non-resonant modes can be, that we have this non-resonant mode in protostellar jets, and therefore we can amplify the magnetic field. Here we compute the magnetic field in the saturation regime, and this is the same plot as before, but instead of plot in the plot that I showed you before, it was the energy density in non-thermal electrons against the magnetic field. Here we plot, instead of the energy density in non-thermal electrons, we plot the energy density in non-thermal protons against the magnetic field, and we have assumed that the energy density in non-thermal protons it is larger by parameter A. That somehow this parameter it is it is a function of this of the spectral index. So we know if we know the energy density in non-thermal electrons, we can estimate also the energy density in non-thermal protons, and we plotted here the energy density in non-thermal protons against the magnetic field line. And this red dashed line, it is the saturation magnetic field. That again, that it is a function of the energy density in non-thermal protons and the shock velocity. And we can see here that at these values we have, or if, let's say, if we assume that the magnetic field is amplified by these Bell instabilities, and it is in the saturation regime where the red lines cross this red dashed line, we have an estimation of the magnetic field in the hotspot. In our assumption, I mean, with our assumption, I mean, let's say that we're assuming that the magnetic field is amplified by Bell instabilities. So we can estimate the magnetic field in the hotspot, and it are these values. And these sources, these numbers here indicate all the sources in the first table that I showed you at the beginning of my presentation. And finally, if we have these non-resonant instabilities, we can also estimate the maximum energy of protons by equating the maximum growth rate with this characteristic time scale. This characteristic time scale, it is the width of the shed, that it is somehow also the size of the hotspot divided by the shock velocity. And if we assume that if this product is larger than 5, that it is the time that we need to really amplify the magnetic field, we can have an estimation of the maximum energy of protons. And for all of our sources, we have maximum energy of protons of about 1 TeV. This approach here, it is the same approach that has been done in these papers for supernova remnants, but we apply the same approach for protostellar jets. For the case of electrons, the maximum energy, it is constrained by synchrotron cooling. However, in order to know this, to really estimate this maximum energy in electrons, we need to know the diffusion coefficient, that is this parameter, this D value here, and this we don't know. However, what we know, it is because these electrons behave as test particles in the magnetic field or in the magnetic turbulence amplified by protons. Then these electrons will diffuse in this small scale diffusion regime, and therefore this diffusion regime, it is larger than the bomb diffusion regime, and therefore the energy density in non-thermal electrons will be smaller than the energy density in non-thermal protons. And this plot, it is to show you that that only in jets, in very, very dense jets, or in very luminous for the case of very dense jets, the maximum energy will be constrained by relativistic Bremsstrahlung mechanism, or in the case of very luminous protostars, the maximum energy can be determined by inverse Compton cooling. However, it is not the case it is not the situation for our sources, and in all of our sources in this table, in our sample, the maximum energy, it is determined by synchrotron cooling, because the magnetic field in the hotspot is quite significant. I mean, it is like of the order of 1 milligauss. And finally, I wanted to show you some predictions for the gamma ray emission, because if we have TeV particles, let's say TeV electrons and protons, then these particles can interact with, for instance, the matter in the jet termination region and produce gamma rays by relativistic Bremsstrahlung and proton-proton interaction. Here I show you only the spectrum in gamma rays due to proton-proton interaction, because it is larger than the emission due to relativistic Bremsstrahlung. So these green lines is our prediction for all these 11 sources. This is why we have there are here 11. It is a bit messy, so there are 11 green lines that are the prediction for our 11 sources of the gamma ray emission due to proto-proton interactions. When the density in the shed termination region, it is due to we use our estimation with the mass loss rate by using this mass conservation across the shed. And we can see that if the density, it is like the density in the downstream of the river shock, I mean, this is why we multiply by a factor of 4, it is this value, then the gamma ray emission due to proton-proton interaction cannot be detected in principle by the Fermi satellite after 10 years of observations. I mean, here I use the sensitivity of the Fermi satellite for these 10 years of collecting data. And we can see that for these densities estimated with the mass loss rate, these sources are not detectable by Fermi after 10 years of collecting data. However, if the density, it is this average density that we estimate by this average density between the lower value it is this m dot and the upper value of the upper limit of the shed density due to this free emission. So if the density it is this average value, then this for 3 of our sources we can have this that we predict that the emission can be detected in gamma rays by the Fermi satellite. There is another way to increase our emissivity in gamma rays by increasing the density, because this emission it is due to proton-proton interaction. I mean, it is interaction of non-thermal protons with thermal particles. I mean, with the plasma, with thermal plasma. And because of termination, as I mentioned before at the beginning of my presentation, we're interested in adiabatic shock, in adiabatic mass disk or adiabatic reverse shock, because we want to accelerate particles here, but these particles then will diffuse to this till this thin layer, thin and dense layer created by this radiative bow shock. So if we have a combination of adiabatic shock, adiabatic reverse shock, and radiative bow shock, then we can use this very dense layer as a target for proton-proton interaction. And this dense layer, it is much larger than 4 times the density of the unshocked plasma, because the compression ratio by this in radiative shocks, it is much larger than 4, and it can be significantly larger as we estimate here. So for the case of radiative bow shocks, particles accelerated in this adiabatic reverse shock can diffuse here and radiate here by proton-proton interaction, or relative brainstorming for the case of electrons. And this situation will significantly increase our emission the emission of the sources in the gamma ray domain. So here we have estimated that this dense layer will be destroyed, let's say, by Rayleigh-Taylor instability, like on a time scale smaller than the dynamical time scale of the shed. So this Rayleigh-Taylor instabilities is a way to mix this very dense layer created by the radiative bow shock with the plasma here in the hotspot. And finally, I want to mention that these protostellar sheds have been studied in the laboratory, with laser plasmas since a long time ago. And this example that I choose to show you now in this presentation, it is a nice experiment for this that it has been done for the case of protostellar shed. And what they see is that the bow shock here, it is like, let's say, fragmented by thermal instabilities, not by Rayleigh-Taylor, but by thermal instabilities. Because in this experiment, these sheds are very radiative. I mean, the radiation it is very large, and therefore this is what they see, that they have some mixing due to thermal instabilities in these laser plasma jets. And concerning the gamma ray emission, I will mention that there are some till now there are no detection of gamma rays from protostellar jets. However, in this study, in this paper, but there are other papers where they find some association between Fermi sources and high mass star forming region with protostellar jets inside. And in this study, they find that 70% of the cases are in 70% of the sources in the sample, they find this kind of this association between Fermi sources and star forming region with protostellar jets. And I want to mention that it was the claim last year of detection of gamma rays by Fermi from these sources. This source HH81 is the one that I show you where we have this polarization data in radio. And in this author, they claim this detection of gamma rays from this source. However, Emma and also Carlos Carrasco, they took this Fermi data and they put this Fermi data together with this here. You cannot see it probably, but because it's very small, in this white. So inside this white square, we have the VLA data, I mean the data in radio of this source. And all this, it is the Fermi data. So it is very, very hard to claim from here that this gamma ray emission, it is coming from this source. So what is our conclusion is that nowadays, again, there are no detection of gamma rays from protostellar jets. However, our predictions show that these sources are very good candidates because even without mixing, I mean, even without this disruption of the bow shock by instabilities, we can have detectable levels of gamma rays. So if then we consider this larger densities due to mixing by Rayleigh-Taylor or thermal instabilities, then this prediction can be much larger than the values here, and then the detectability by Fermi, it is much more promising, let's say. And I hope that in the next few years we will have a clear detection of gamma rays from these sources. And finally, my conclusions are that these jets from high mass protostars we know that there is an increasing population of non-thermal emission from these high mass protostellar jets, and magnetic field that we estimate it is of the order of 100 microgauss or 1 milligauss in some cases. So this magnetic field cannot be the magnetic field from the jet, and this is why we need some kind of local amplification of the magnetic field. In our model, we discuss magnetic field amplification by Bell instabilities. And if the magnetic field is amplified by Bell instabilities, we can reach these values that we need to explain this synchrotron flux measured in radio frequencies. And also, we estimate maximum energy of electrons and protons of the order of 0.1 and 1 TeV in all of the cases. And finally, these GeV and TeV particles interacting with dense plasma in the termination region of these protostellar jets can produce detectable levels of gamma rays in the Fermi domain. And if we detect really these gamma rays from these sources, it will be very useful, let's say, for understanding particle acceleration in this plasma, and this very dense and not very fast jets, and also a magnetic field amplification in this region, because this model of magnetic field amplification by Bell instabilities, it has been very well studied in the context of supernova remnants, but not in these dense plasmas. And this is what we are doing now, like applying this mechanism to protostellar jets. And that's it. Thank you very much.
Okay, thank you, Anabella, for this great talk and very clear. And we have a lot of questions. We start with Betch.
Oh.
You can...
Hello, Anabella. Here is
Hello.
Silvia Delfino speaking. How are you? How are you doing?
I'm fine. I'm in Prague. It's dark now. It's almost 8 p.m.
Oh, yeah, that's true. Annabella, I have a comment on, because, you know, protostellar jets, low mass protostellar jets are strongly radiative cooling jets. They do not behave as adiabatic jets. And this because, and this actually was what motivated several groups, including ourselves, in studying radiative cooling jets and simulations of radiative cooling jets in order to explain the emission structure of these jets, right? So as you showed, Blondin has studied these limits exactly to compare how an adiabatic jet, for instance, jets produced by agents, should be compared with radiative jets. And it turns out that protostellar jets from low mass, high mass protostellar jets is another story, because they are very short-lived, very unstable, so almost no observations of large mass protostellar jets. But low mass protostellar Herbig-Haro jets, AGH jets, they are extremely radiative cooling. And this because it's the only way to explain the observations of forbidden lines, H-alpha emission, and even molecules that are produced by these jets. And it turns out that this energy is all, it's radiative cooling. So the energy of the shock is let's say, depleted in these thermal processes, right? And also, you showed an example of laboratory protostellar jet where you see this thermal instability. Mm-hmm. Yes, this thermal instability also occurs. It's a combination of non-uniform radiative cooling that causes this thermal instability that causes fragmentation. And this also has been thoroughly studied by means of numerical simulations made by our group, including our group, Raga in Mexico, and Blondin, and I mean, there are several people who worked on these radiative cooling shocks and detected these non-thermal instabilities that break and fragment the shock. But again, this is mediated by radiative cooling. All these shocks are radiative cooling with a lot of entrainment and turbulence, with a big cocoon formed around the protostellar jets. So I suspect that if this emission, high energy emission, is associated to regions of massive star formation, so perhaps they are more associated with large mass stars with very unstable jets that survive just for a little and are very hard to observe, right? These could be more adiabatic shocks and therefore produce non-thermal radiation, because as long as they are radiative, it's very hard to connect. And the other possibility is also that these shocks, these radiative cooling shocks, are interacting with clouds or supernova remnants, and they can excite, these interactions can excite the formation of shocks, new shocks, adiabatic shocks that then could produce cosmic rays and all this sort of high energy emission. But so probably there is, you know, a missing gap in these observations that we have to understand better. Could you comment on this, Anabella? Because I'm sure that you...
So this work is focused on high mass, in jets from high mass protostars.
Yes,
because,
but for instance, Herbie-Haro 88, 82 is how big is the mass? Because I think this is low mass.
Which one, sorry?
Herbie-Haro 80, 82 that you mentioned in the end of your...
This is high mass. This is very, very high mass. The luminosity, I think it is more than 10 to 4. The luminosity of the central protostar. It is.
The luminosity of protostellar jets is big as well. I'm talking about the mass of the jet itself. If it's high mass, because again, if they have a radiative thermal emission, if they are reaching thermal emission, right? Because these high mass, there are a few cases simply because they are destroyed very, very fast, right? There are a few cases with no thermal emission, yes. So you are talking about only these sources that have been detected synchrotron, VLA.
Yes. Because there we know that there are, there we know that there is a population of non-thermal electrons because we see synchrotron emission. Then the second step is this energy density that we need here in non-thermal electrons to explain this synchrotron flux in radio. This energy density in non-thermal electrons, it is much larger than the energy density in the environment. This is why we need local acceleration of electrons. So these electrons are locally accelerated, and this is why. So this let's say this approach that it is somehow like, you know, in this all supernova remnants, they say, okay, these shocks are radiative and therefore they cannot accelerate particles, and then this emission is just due to compression of the plasma. But this is not our case. Our case, it is we need this local acceleration of particles because the energy density that we need to explain this flux in radio, it is much larger than the energy density of cosmic rays in the environment. And then here we estimate what is the shock velocity that we need for the shock to be adiabatic.
I know this argument, but how many of these massive protostellar jets have been detected?
So in radio, like a non-thermal radiation in all these sources?
Non-thermal,
Yes. In all these sources, and there are like probably 10 more, because these are all the sources from these two papers, but then we have also these other canonical sources, like these sources that they have been studied by Luis Felipe, also this one, the serpents,
and then
like 20.
And then that final catalog that you showed with the Fermi, are all those objects high mass protostellar objects?
These are high mass star forming regions with protostellar jets inside.
So those correlations are all with these highly massive protostellar.
Yes.
Right.
Yeah.
And do you know the mass range? Sorry, too many questions.
Maybe we can continue discussing. Let's just pass to the next, and then we come back to you. But can it be?
No, it's okay. I mean, it's only to know the mass range in this catalog.
And the mass range of what?
Of these massive protostellar.
This I don't remember.
Okay. No, that's for all. Thanks a lot, Anabella. Yes, I'm glad that they are all massive.
No, Juan?
Here. Hi, Anabella.
Hello.
It's very good to see you, at least digitally here. I think the first time I met you was when you were doing postdoc in Mexico. I have two questions. So can we conclude that the Bell instability is the one that best works for magnetic field amplifications in these protostellar jets than, for instance, in comparing with other magnetic amplification mechanisms?
Like what, for instance?
For instance, turbulence-induced amplification. Because, for instance, if I correctly understood, with this mechanism, this is the cosmic ray streaming that amplifies the magnetic field, right? But I've seen that there is other types of magnetic field amplification. So I am guessing that this is like the best one the one that works better in these objects.
Well, for instance, you can have another typical amplification mechanism in astrophysics is this Bible instabilities. However, these Bible instabilities cannot work here because even when we have this large Mach number, these Bible instabilities are very low scale of magnetic field is amplified on very low scale, and therefore it decays very quickly. So with this Bible instability, we cannot explain these large, let's say, synchrotron emitters with this large magnetic field. And then you can have amplification probably by, let's say, by like a large scale instabilities, like the plasma moving. But I think this will work more like when the plasma escapes from the hotspot.
Okay. Thank you. And I have another question. You were discussing detectability in the gamma ray regime, but what about X-rays? Do you have any comment if there's possible detectability in X-rays? Or
yeah, so I didn't show you here the complete spectral energy distribution, but there are some X-ray emission from these sources. I will show here. So this is this source HH8081, and here you can see that in this, for instance, this is HH81, and you can see in green radio emission and in orange X-ray emission.
Okay.
Also in HH80 again, X-rays and synchrotron emission in green and in orange and white X-rays. And you can see it is in this paper we model this X-ray and X-ray emission from this particular source.
And this X-ray emission is of what is the origin of this?
Thermal. So in our model, this X-ray emission is thermal emission produced in the bow shock. I mean, we have again a radiative bow shock and an adiabatic reverse shock. So in the adiabatic reverse shock, we accelerate the particles and produce this synchrotron emission. And in the bow shock, we have this, we compress, we heat up the plasma and produce this thermal X-ray emission. So this is our model. However, in this paper, this Lopez Santiago et al. 2013, they claim detection of non-thermal X-ray emission from the same source. And it's blue dot here, but so we have some reservations concerning this result.
Okay, if I correctly understood, you were modeling the X-rays with thermal emission.
Yeah.
And then they find an indication for non-thermal emission in X-rays. But this especially corresponds also to the bow shock that you were discussing.
So let's say here in this source here, it is this. I think it is this source. It is somewhere. I think this blue dot, that is the non-thermal X-ray emission in this paper, it is somewhere here. And somehow that there are no synchrotron emission in this that is coincident with this non-thermal X-ray emission claimed by this author. This is why we have our reservation, because if we see if this emission it is really coming from this hotspot, we should see also synchrotron emission in radio, but we don't see it. So this is why it is quite weird for us. This claim.
No, but my question is just simply because you were mentioning that probably proton-proton interaction would be like a possible mechanism. But you know, this proton-proton also release secondary electrons, and probably the secondary electrons could have a counterpart in X-rays. And just my comment is that.
Yes, yes. So in this so here it is the emission only of the primary protons, but then so in the next paper we want to also compute the emission due to secondary particles. I mean, you know, from this proton-proton interaction, we have this secondary electron positron pair that also they can produce electronic emission. It is not considered here, but yeah, we will do it in the future. Yeah.
Thank you.
I have two very short questions. My first is in slide 13, you commented that it's uncertain the ratio between the widths of the emitter and the jets, and you need this ratio to constrain some parameters of the jets.
Sorry, which slide?
Maybe the previous one. 12.
I cannot hear you very well.
I think the previous slides, or is this? You talked about the ratio between the emitter, the width of the emitter region and the width of the jets. Yes, because there can be a factor there. It's uncertain, this factor. Is it possible for you to estimate this factor from the simulations that exist for these simulations by Betty and the Boots showed, or it's necessary to make all the radiative?
No, I think so. Here we took this value. I mean, the width of the shed, we took it from the synchrotron emission, I mean, from the observations. But as you can see here, I mean, if the synchrotron emission, it is somehow here. So this is a sketch. But if you don't have good resolution in radio, then you will see that your emission it is much larger than the shed. So then estimating the width of the shed just with the size of the radiometer, it is tricky.
All right.
But so with simulations, yes, we can constrain this parameter much better.
Right. And the second short question is about the Bell instability. Because is it enough that you have conditions for the Bell instability? Because if it's non-resonant, the non-resonance part of the Bell, it's much smaller than the resonance length for trapping the highest energy cosmic rays. So you need, besides to trigger the Bell instability, that it grows to larger scales, right? Or no, it's enough, it triggers, and it's by sure it will amplify in scales until it traps high energy protons.
I don't know if I follow this your question. So what we have done, so we didn't have any. Our estimation is very simple. So we only compute the maximum growth rate that is here, and we solve the dispersion relation. And it is so we can see that we have in all the cases we have this non-resonant branch or this non-resonant regime. Then there is an issue that if the plasma it is not completely ionized, then we have something like this, that the maximum growth rate will be lower.
All right. But the limit of this maximum growth rate is about the gyro radius of the tera electron volts protons.
So here it is, yeah, I understand. So this maximum growth rate, it depends on the energy of the particle. So here it is for 1 GeV particle, yeah. So this calculation is for protons with 1 GeV. But then it depends on how it is your distribution of protons. And in our, like let's say in Supernova Remnants, this proton, the distribution in protons, it is like, let's say E2-2, the canonical one. So here we have like between minus 1.8 and minus 2.3, let's say, and our range for distribution of non-thermal electrons. And then we assume the distribution of non-thermal protons is the same. But because we don't have any information about non-thermal protons, we just say, okay, if we have non-thermal electrons, then we should have also non-thermal protons, because in principle this acceleration mechanism is the same for electrons and protons.
Great. Thanks.
And we assume that the protons follow the same power law as electrons. And the power law in electrons, we know it from this synchrotron data.
All right. I have more doubts about some details, but we can talk a bit.
Okay.
Thank you.
I think Pankaj has some questions.
Okay, so can you hear me?
Yes.
Yeah, so on your slide number 9, so
This
you
one?
said that yeah, exactly. So you said that the central source is thermal, while others are non-thermal. The index, I mean, so are these sources not compact like AGNs, that the index should not be positive like it's in the central part?
Can you repeat, please?
So, I mean, you said that the central source is thermal source.
Yes, because it is positive, the spectral index.
Yeah, but so that's what I am asking. Like in AGNs, if the core is compact, we see positive slopes because of the self-absorption. So, I mean, based on just spectral slope, how are we confident that this is a thermal emission? Just curiosity. I don't know, because I am from AGN background.
No, so here it is just, I mean, this free emission, let's say, it is usually if you model the free emission, the slope is positive. And if you model the non-thermal emission, like a synchrotron, the slope is negative because it is somehow related with the slope in non-thermal electrons, that it's negative.
Yes, I agree. But the non-thermal electron, if it is optically thin,
yes,
the slope is negative and related to the directly with the spectrum. But if the source is compact and the synchrotron self-absorption is there, I mean, it's optically thick, we also get a positive slope like the one.
But this synchrotron self-absorption, it is at much lower frequencies, not in this range.
It is
outside this range. Yeah.
Okay, fine. So, so in all the calculations, it's basically the equation used for synchrotron is actually for optically thin, right?
Yeah.
Okay. So, and the second thing is about this slide number 12.
This one?
So you mentioned, yeah, exactly. So you mentioned that you choose alpha value between the 0.45 and 0.78. So is there any particular reason for that?
No. So this value here, I should put a minus. So to be consistent with our previous discussion, that is.
I got it. That is optically thin. Yes.
So this should be, there is a minus missing here, and I choose these values because in the paper where this data is published, they have so for them all the sources with a spectral index lower than minus 0.1, it is non-thermal. So we made our selection a bit more strict because minus 0.1, minus 0.2, it can be really, you can really have mixture between thermal and non-thermal. So this is why let's say smaller than minus 0.3 to be really sure this non-thermal. Because minus 0.2, minus 0.1, it can be really tricky, let's say.
And just a quick question on the next slide. So how do you, how do you measure the mass loss rate? You mentioned that
we took it also from these papers. They estimated, and they did it. Usually, the way to do it is with the thermal emission here at the base of the shot.
Okay.
They can compute the mass loss rate. There is a canonical way to do it And but we took this data from this paper. I mean, from here, they computed. But usually, yeah, the ways with the thermal emission at the base of the shaft.
Okay, thank you.
You're welcome.
Okay, I have a short question. You mentioned that there is polarization measurements only for one object,
Yes.
H81.
Yes.
So what's the degree of polarization? Do you remember?
I don't remember. I don't remember now.
Because you would expect polarization in all of them, I guess, but.
Yeah, but so here they did it with this very low resolution data. I mean, with VLA data in the C configuration, that it is not the one with the higher resolution, and they measured this polarization. I don't remember now the degree of the polarization for this particular source, but then they observed the same source with more resolution, and they didn't see any polarization.
Okay.
And yes, till now is the only source, and this low resolution data where you can see this polarization measurements.
Okay. Anabella, thank you again for the talk. Let's continue discussing this. We will finish just the transmission now.
Yes.
But if you can stay a little bit more for
Sure.
More discussion and people can talk freely. So thank you everyone following in YouTube. And who can stay, who wants to discuss, feel free to stay. And you can open your microphone. So, Richard, você pode encerrar a transmissão.